Hello everybody. This is Professor Coppola broadcasting from the nation's capital, and I'm trying something new for this review session for our next exam. The chapters involved will be Chapter 7 Part 1 and Chapter 7 Part 2 and then Chapter 8 and Chapter 9. None of Chapter 10 will be on this exam. I'm using Loom, which is a different service, so let's see how it works. So, first major point. In the quantum theory tells us that light behaves as a wave and a particle. And the same is true of electrons. Electrons behave as both a wave and a particle. Okay, let me go to slide 6 here. Here we have some equations that you may need to use to solve some problems. I will be giving you these equations on the reference page, which will be the front page of the exam. So the first equation, speed of light, which will be given, equals to the wavelength, lambda times nu, the frequency. Speed of light will be given 2.998 times 10 to the 8 meters per second. So using that equation, if you know one of the variables, you can find the unknown variable. Now, there is another equation that you'll need to use. E is equal to h times nu, excuse me, and nu is frequency. H will be given, which is 6.6262 times 10 to the minus 34 joule seconds. Okay, so if you want to combine the two equations, then you have this equation down here. Let me try something here. You can try that equation down there if you'd like. But otherwise, as I did in class, you can use this equation to find one of the variables and use this equation to find the other variable, or vice versa. Okay? So just as we did in class. All right. And as always, you should know all the terms covered in these chapters, because there will be matching. This time there'll be 15 matching questions, a set of 10 and then a set of 5. And now what I'm going to do is go to slide 18. So this is one of the terms you should know, and it's a wave property of light. Refraction is the bending of light as it passes from one substance to another. Okay, and you've all seen this before. Let me just get this out of the way. This is the first time I'm using this, so it's a little different. Come on, a little different. I'm trying to get the pen, but it won't let me do it. Oh well. And then diffraction, which is the bending of light as it passes through a slit. That's another wave property, and that's going to be found in the next slide, right there. Okay, so the bending of waves as it passes through a slit is called diffraction. And then we're going to go to, let me see if I can move this up a little. Oh, wait a second here. There you go. Okay, let me see if that makes it easier. Yeah. Okay, and now we want to go to, as I say, this is the first time I'm doing this, so let's go to slide 23. Remember that if you heat up an element, each of the elements gives off a different color of light. If you take that light and pass it through a prism, you get these spectral lines. Again, this is a wave property of light, and every element can be identified by a unique set of spectral lines. And that's why we're able to identify elements in outer space by looking at the light. Okay, let's go to slide 27 right here. And this is the photoelectric effect. You should know what that is. Electrons are emitted from the surface of metal when light strikes it. Now the light has to be of a certain frequency. But in any event, this is how the solar calculator works. The light hits it and then it produces the electrons. The electrons then produce electricity. Okay, let's go to slide 32. There we go. Slide 32. One thing I want to emphasize here, well, these points, but if energy is absorbed by the atom, the electron will move to a higher energy level. Okay? So it's going to move to a higher energy level, and let me see if I can show you the picture. Yeah. So if you add, you could have an electron and n equals 1, you add energy, it's going to jump up to a higher level. All right, another equation that you will need to use to solve a problem is de Broglie equation. And it was de Broglie that discovered the wave nature of an electron. Now again, the electron acts as a wave and a particle, but when it acts as a wave, he came up with this equation to determine the wavelength. So you just take h, which is Planck's constant, and divide it by the mass in kilograms times the speed. So basically this type of equation is a plug and chug. You'll have the equation and you'll be given the mass in kilograms and the speed, and h will be given, Planck's constant. You plug in the numbers and solve it. So you need to know how to, the easiest way to do it is to put the scientific notation in your calculator and do the calculation that way. Okay? So if you know how to do that, this will be very easy. And I'm also going to give you this equation on the reference page of the exam, so you don't have to memorize it. Okay, and this is the first point I made today. Both the electron and light can act as a wave and a particle. There I am. Hello. All right. And let's go to slide 38. And this is just a problem using this equation that I just talked about. Let's see if this will work. Yeah, there you go. So this is a problem using this equation, and you just do the plug and chug. Plug in the numbers and do the calculation. Okay? So you'll see one problem like that. All right, and then we hit this famous guy. Everybody has heard about this guy. Slide 40, Mr. Heisenberg. So you should know this for the matching. The Heisenberg uncertainty principle. You can't measure both the location and the speed or momentum of an object with equal accuracy, because the better you measure it, then you affect the speed. So you affect this location. So you can't measure both the location and the speed. So just know that that's called a Heisenberg equation. It's a very famous equation. Okay, going to the next slide, 41. So again, these are the equations. You'll have to solve problems. You don't have to memorize them, even though I said you did. I'm changing, and I'm putting these on the reference page. So you just have to know what the symbols stand for. C will be given, speed of light, and h will be given, okay? So you'll have problems using each of those equations at the end of the exam. Okay. Let's go to slide 49. And then remember, we learned our secret code about quantum numbers. So the first quantum number that we talked about was the easiest one, n. So n goes from 1 to 7. Imagine the periodic table. These basically 7 shells around the atom. But remember, when you get to the transition elements, the D block, n goes down by 1. Okay, so you can start off here at 4, but then when you reach the transition, the n becomes 3. And once you finish that, then it goes back to 4 again. All right. Then we talked about the meaning of an orbital. Very important, very important. So what's an orbital? And again, you could see this in a matching or true and false questions. I'm going to have some matching, some true and false, some multiple choice. So I'll have a variety on this exam. So an orbital is a potential space for one electron or for an electron pair. And we can represent it just as an underline, and that would be one electron, that would be a pair. Or we can represent it by boxes, which is better, but it just takes longer to draw them. And sometimes you see them represented as circles. But again, the orbital can have one electron, or at most it can have 2. So an orbital is a potential space for one electron or for an electron pair. And then we start to get wild, don't we? We get into the shapes of the sublevels, which is the second quantum number, okay? L. And what's the shape of the s orbital? It's a sphere, and you might see a picture of it, or you might be given a verbal description. You should know that it's a sphere. P orbital is a dumbbell, where it has these two lobes. The d orbital is a cloverleaf shape, and the f we're not really going to work with. I'm not going to give you any questions on the f. There's actually several shapes for the second quantum number. And then in the next slide, we get the value of L. Remember, this code is all going to be in numbers. So n can be anywhere from 1 to 7, and L can be anywhere from 0 to 3. So for the S block, L is going to be 0. For the P block, L is 1. For the D block, L is 2. And the F block, L is 3. So that's the second quantum number. Okay, I think that's slide 54. Now we want to go to slide 55. This is a good review here. The s sublevel can only have one s orbital. L is equal to 0. It's a sphere. The p sublevel has 3 orbitals, which can contain a maximum of 2 electrons in each for a total of 6. L is equal to 1. It's a dumbbell. D sublevel can have 5 d orbitals, each with a maximum of 2. And it's L is equal to 2. It's cloverleaf. And F has 7 orbitals, and L is equal to 3. Okay, that's 55. And now we go to our beautiful, beautiful, beautiful block chart, which makes life so easy for you. So we have the S block, and for our purposes here, helium really fits in with the S block because the electrons go into an s orbital. Okay, so that's the S block. L is 0. P block over here, there's 6 elements. L is equal to 1. The D block, there's 10. L is equal to 2. And the F block, L is equal to 3. There's actually 14, but we're not going to work too much. I'm not going to ask any questions about the F block because I think you have enough to learn, so we don't need to make it too complicated. Okay. Then we go to slide 59. And in slide 59, we get to the shape of the p orbital. There's 3 of them, and they're perpendicular. And that's where we end up with the m sub L quantum number. Okay, because there's 3 shapes here. And you could also show it this way. The 3 orbitals perpendicular to each other. Now, to figure out L, we just have to remember, or m sub L I should say, m sub L, the third quantum number, goes from minus L to L. So for S, it's just going to be 0. It's going to go from 0 to 0. So m sub L is 0, 0. When L is equal to 1, the m sub L is minus 1 to 1. And it repeats twice because there's 2 sets of electrons. When L is equal to 2, for D, it's minus 2 there. So you'll know, for example, if it only includes from this range -1, 0, plus 1, and I say the m sub L is -1, 0, plus 1, you know it has to be the p orbital. Or if you see a -2 or a +2 for m sub L, you know it has to be the d orbital. So again, it's just going to be the L minus L to plus L. Remember that for S, L is 0, for P, L is 1, for D, L is 2. S block is 0, P block 1, D block 2. So m sub L is just a -L to plus L. Okay, and then remember our electron spin, which is our fourth, going to slide 64, our fourth quantum number, m sub S, standing for spin. Remember, they have to be of opposite spin, and we normally indicate that 1 arrow up, 1 arrow down. It doesn't matter which is first, as long as they're opposite. Or in our code, in our secret code, we indicate the fourth quantum number with a +1/2 or -1/2. So the first electrons in each orbital are +1/2, and the second electrons in each orbital have to be opposite, so they're -1/2. And so now we put it all together, slide 71. So let's go to slide 71. So this little baby puts it all together. Notice here on the exam you may want to draw a sketch of this on scrap paper, but there's only going to be maybe 2 or 3 questions on this, so I wouldn't put too much time on it, but hopefully you'll be able to understand it. So n is the principal quantum number. N goes from 1 to 7, although the D block is always one less. L, again, you don't need to know the name. So L, remember, for the S block is 0, for the P block is 1, and the D block, L is equal to 2. And then M sub L for the S block is 0, 0. M sub L for the P block, it goes from -1 to 1. So -1, 0, plus 1, -1, 0, plus 1. It has to repeat twice because there's 2 sets of electrons in each orbital. And then for the D block, N sub L is -2, -1, 0, plus 1, plus 2. And then repeating -2, -1, 0, plus 1, plus 2. Again, it has to be from -L to L. And it repeats twice because there's 2 sets of electrons. And the last quantum number is M sub S, the spin. So the first column, the first family is +1/2, the second one is -1/2 in the S block. In the P block, the first 3 columns are +1/2, the second 3 columns are -1/2 for the second pair of electrons. And then for the D block, the first 5 are +1/2 spin, and then the second set of electrons are -1/2. Okay, then I'm not going to go through it now, but then I go from slide 72 to 79. I give you several examples. So you should be able to go through those examples and get the right answer, come up with the 4 quantum numbers. And by the way, going back to this slide, for any electron there are 4 distinct quantum numbers. No 2 electrons can have the same 4 quantum numbers because the last one, the M sub S, they have to be opposite spin. So no 2 electrons can have the same 4 quantum numbers, or for any electron there are 4 distinct quantum numbers. Okay? And I gave you a handout to explain why knowing the quantum numbers is very useful for chemists. Okay, and that brings us to Chapter 7, Part 2, where we start talking about the way electrons are configured around the nucleus. I told you they're like a crown of stars in a very elaborate arrangement. And we also look at trends in the periodic table. Now I'm reviewing Chapter 7, Part 2. Excuse me, sorry about that. Okay, so let's see if I can get to slide 2. If not, I go like this. So again, a review. And it's good with this material to look at it see the same thing several times. Okay, so this is a nice review. The S is a sphere. It has 1 orbital. P orbital, the 3 orbitals. It's a dumbbell. D orbital is a cloverleaf, 5 orbitals. And the F has many shapes. I'm just showing 1, 7 orbitals. And each orbital has a maximum of 2 electrons. And then if you want to look at the maximum number of electrons in each subshell, well, S has a maximum of 2, P has a maximum of 6, D a maximum of 10, and F a maximum of 14. Okay, let's move to slide 8. Let's see where slide 8 is. Let me just do it this way, it's easier. There we go. Now, this is my homemade slide just to give you the idea that here's our nucleus right here. And in the first energy level, n equals 1, which is the first row or period in the table, you can only have an s orbital. That's it. In the second row, you can have an s and a p. In the third row or third period, you can have sp and d. In the fourth and higher, you can only have s, p, d, and f. There's no other sublevels other than that. And notice that the s in the second level is farther away from the nucleus than the s in the first level, and it's considered to have more energy. And the s in the third level is farther away than the other levels, and it has more energy. And the same thing for the fourth. It's farther away, and it has more energy than the other s orbitals. And the same thing is true for for the p's and the d's and the f's. Excuse me. And that's why they're called energy levels, because each ring has a higher energy. And as I told you, for an electron to jump, it has to absorb energy to jump to a higher energy level. Okay, now let's see, slide 9. We're going to look, you need to know this for the matching. What is the off-ball principle? Electrons fill orbitals of lower energy first before filling orbitals with higher energy. So here you can see the 1s gets filled first, that's lower, and then the 2s, and then the 2p. And by the way, this is an orbital diagram. Remember, it has to be one electron in each orbital first before they pair up. Okay, so that's the off-ball principle. You should know that for a possible matching question. Okay? All right, let's go to slide 11. Let's go to slide 11. Okay, so here we come up with the electron configurations. It's a shorthand to show how the electrons are arranged around each atom. And as I told you, it's quite amazing, the order and the pattern that you see here. And remember that the sum of the superscripts is going to be equal to the sum of the electrons, which is going to equal to the atomic number. So the atomic number tells you the number of protons, but in a neutral atom, it tells you the number of electrons. So just knowing, adding up these numbers, 2 and 2 is 4, 6, I know right away it's 10, and 10 is going to be neon. But also, considering the blocks, you can tell, well, if the 1s2 block is filled, then 2s2 is filled, then 2p6, then it's going to be neon. So there's different ways you can get at that. And again, this tells you the first number in front is the energy level, or the shell, or corresponds to the first row in the periodic table. This is the second row in the table, and so on. And then S is the subshell, and then the superscript is the number of electrons in that subshell. Okay, let's go to slide 13. Okay, so this is the way the electrons are filled following the off-ball principle. The lowest energy are filled first. So the 1s gets filled, then the 2s and the 2p, the 3s, the 3p, the 4s, and then when you get the transition, D is lower energy than P, so they go into 3D first and then 4p, and so on. And that's about as far as I'll go to the 5s. I'm not going to go into the 6s and 7s, but what you notice is that the 4f is lower than energy than the 5D. And notice that the n is minus 2 here. So if that's 6 minus 2 is 4, and this is minus 2, 2, that was 7, so that's 5. But I'm not going to talk about 6x and 7s. We'll just do the first 5, okay? And just remember that when you get the 5s, and then when you get the transition, it becomes 4d and 5p. And if you look at the block chart, it should be easy to write the electron configurations. Okay, let's look at the next slide, and this would be writing out, this would be the order of filling as you go through the entire periodic table. Okay, and this puts it all in one line. Okay, now what I'd like you to know, in slide 14, I went through some examples, so you should know how to write the electron configurations for each of these elements. And then also in slide, let's see if I can get to slide 18. Slide 18 was another example. You know, so I'm saying write the electron configuration for an atom that has 7 electrons, so you should be able to do that. And here's another example with silicon. Write the electron configuration for silicon. Of course, first you have to find out where silicon is, and you can see silicon's right here, and you should be able to do that. If you need help, contact me anytime. All right, another principle, 2 other principles that you'll need to know for matching. The Pauli exclusion principle, which we already know but we haven't given it its name. The Pauli exclusion principle says no two electrons can be in the same orbital with the same spin. Okay, so they have to be opposite spin, or you can say, another way to say that is no two electrons can have the same four quantum numbers. Remember, the quantum numbers are n, l, m sub l, m sub s. Hund's rule basically is half filled first. You have to have one electron in each orbital first before they pair up. So here, once all the d orbitals have one orbital, then the next electron, if there is one, then it's going to be paired up. And that's called Hund's rule. So these, on this chapter here, on this slide here, which is slide 20, I just give you some ways to remember those. But you should, like for the matching, you should know the Pauli exclusion principle, you should know the Hund's rule, you should know the off-ball principle, you should know the de Broglie wavelength, you should know the Heisenberg, those kinds of things. You might see those terms. It's a good idea to make a list of all the terms that are mentioned in these chapters and make sure you know what they are. And then for more practice, this is more practice, which I won't go over now, but pardon me, it's the electron configuration for cobalt, and then you should be able to do that. Excuse me, so you have to identify where cobalt is, and then based on the blocks, you should be able to write the electron configuration. So that's slide 21 and slide 22. So here I show the orbital diagrams. And the advantage of the orbital diagram is it shows you which orbitals only have one electron, which is going to be, as you know, is going to be important when we get to paramagnetic and diamagnetic. Okay, so here we have the orbital diagram, and then we have the electron configuration. Okay, and as I say, an easy way to tell what element this is just add up the electrons. 2 and 2 is 4. It's 10, 12, 15. Which one is 15? It is phosphorus. It's hard to read there, but it's phosphorus. Or you can just follow the order in the blocks, and you'll see that you'll end up here. So this will be 3p1, 3p2, 3p3. Okay. Now, because chemists are lazy, they like, actually, what do I show here? Oh, this is, let me show this first. So this is just showing both the orbital diagrams and the electron configurations, so you should be able to do this. These are the elements in the second row or second period of the table. And then the abbreviation, which is nice because we're lazy chemists, we don't want to write all these electron configurations out. So we come up with this system. We use the abbreviated by, let's say you're talking rubidium here. So I find rubidium, there it is, right there. And then the abbreviated electron configuration is you find the previous noble gas krypton, put brackets around it like there, and then what follows is you're now 1, 2, 3, 4, 5, and it's S, so it's 5s1. So you should be able to write abbreviated. And I give you in the slides 26 through 29, I'm not going to go through them now, I give a number of examples of writing abbreviated electron configurations. So you can go through those, you should be able to do that. It's easy, it's really easy. You just have to identify the previous noble gas and then write the remaining electron configuration. Okay, let's go to slide 31 and we get the periodic trends. I'm just going to highlight a few. Let's see if that's not going. Let's see, there we go, slide 31. There we go. So slide 31. First thing is that the reason why elements are put in a column, and Mr. Mendeleev from Russia was the first to do this, is they have similar properties. Hydrogen is not included here, by the way, because hydrogen is an oddball. It's in a class by itself. But anyway, the rest of these alkali metals, they're all very similar. They're soft and easy to cut. They have the same oxidation numbers. They form the same type of ion, +1. They're very reactive. They're silvery looking. And the reason being is because they have one valence electron in the outer shell. All these guys have one valence electron. and that's why they have similar chemical properties. So the valence electrons determine chemical and physical properties. Okay, now very important, I want to emphasize this. You should be able to determine which atom is bigger. So if I give you two different atoms, you should be able to tell me which one's bigger and which one's smaller. And if you, as I said, my colleague, my former classmate from Harvard Medical School who had a photographic memory, he could take a picture of this in his mind. But you remember, as you go down, they get bigger. As you go from left to right, they get smaller. And you should know the reason why. As you go down, you're adding a new shell, so it's bigger. Now, let's say this is period 2 here, okay? We're second row. So it's the second shell. Why do they get smaller? Because you're adding an electron in each case, but you're also adding another proton to the nucleus, which keeps increasing the nuclear charge and has increased drawing power. So fluorine has the most in that period, most protons, and it really pulls in the electrons. Okay, so you're increasing the nuclear charge. It's the same outer shell, so they get pulled in and becomes very small. Okay, so you should be able to compare different atoms and see which is bigger and which is smaller. Okay, let me go now to slide 39. Whoops, why doesn't it go? Okay, sometimes it gets stuck. That's okay. Okay, slide 39. Why is it acting like that? I don't know. Oops, it moved. It's not, oh well, it's not in view. Let's see, why is it doing that? Can I do anything about it? Well, this is a glitch. I'm sorry, you can't really see the slide very well. Let me see, can I move this? No. Can I move that guy? It looks like I can't. No. Anyway, well, I'll just tell you what's on the slide. This is slide, sorry about that. It's not cooperating, but this is the one on magnetism. Remember, diamagnetism, it's repelled by a magnetic field and all the orbitals are paired. Whereas, and this is cut off here, paramagnetism, by the way, this is slide 39. Paramagnetism, property where a substance with unpaired electrons are attracted to a magnetic field. So paramagnetic, attracted to a magnetic field, half-filled orbitals. Diamagnetic, repelled by a magnetic field because all paired orbitals. Okay, and then I gave some examples in slide, let's see if it'll show here. So here, yeah, let me just show this. So slide 40 does show properly, and we can see that the ones that have the arrow, they're paired, and so they're diamagnetic, repelled by a magnet. And then the next one, where I have the blue arrow, they all have at least one half-filled orbital, and those are paramagnetic. They are attracted to a magnet. Okay, that brings us to chapter 8. By the way, we're about halfway finished. It's about 30 minutes so far. Hang in there. So, now what I'd like to do is highlight important things from chapter 8 on chemical bonding, which we know is the way that atoms are joined together to form molecules and compounds. Here's some terms you should know. What is a bond? It's a force that holds groups of atoms together, so they function as unit. Bond energy, the energy required to break a bond. Ionic bonding, which you should know very well, results from electrostatic attractions of closely packed, oppositely charged ions. Okay. And then we got into polar, well, excuse me, not yet. Ionic compounds. So here's an example. Sodium chloride, notice in the shape of a cube. For every positive ion, sodium, excuse me, you have a negative ion. And the electrons are transferred, from the sodium to the chloride. And so the positive attracts the negative. It ends up in a crystal structure. And then we got into the polar and nonpolar. So remember what nonpolar is? Two identical atoms share electrons equally. And just for fun, I'm not going to ask you this, but the memory devices have no fear of ice-cold beer. These are the diatomic atoms that exist in nature. But the point that I'm making here is, because of the same atom, they're all nonpolar, equal charge distribution. Polar covalent bonds, on the other hand, are not at the North Pole, but they have a positive pole and a negative pole, also called dipoles. They have unequal sharing. So one of the atoms has a greater pull on the electrons. So you can see here, remember we talked about this, fluorine is more electronegative. The electronegativity is the degree that it pulls on electrons toward itself. And so the electrons move toward fluorine, and so you get a partial positive and a negative, and you get two poles, and that's a polar covalent bond. Let's see here. Slide 7. I'll give you the answer, but it says, what type of bond is formed when electrons are unequally shared by nuclei? It's a polar covalent bond. Okay, slide 8. I give you the definition. Electronegativity is the ability of an atom to attract or pull toward itself shared electrons. Each atom has a unique electronegativity value, and Mr. Linus Pauling developed this scale. He Nobel Prize winner, and you can see that each atom has a unique electronegativity. The highest electronegativity is fluorine, 4.0, francium is 0.7. Now, by the way, I'm going to have this on the front page of the exam, okay? So this will be a reference page for you to use, and you can refer to it during the exam. And one of the reasons you might want to refer to it is on the next slide. Let me see if this is going to work. There we go. So remember what I told you. If the electronegativity difference is 0, it's nonpolar covalent. If the electronegativity difference between two different elements is between 0 and 1.7, it's polar. And notice that this is going to be a nonmetal with a nonmetal. So if it's 0 difference, if it's the same atom, like Cl2, nonpolar. If it's different, nonmetals C and O, they have different electronegativities. It's between 0 and 1.7. And then if it's a metal with a nonmetal, the electronegativity difference is going to be greater than 1.7. So that's one of the things, that's one of the reasons why you might want to refer to this chart, so you can look at the electronegativity numbers. And by the way, notice something here which I'm going to talk about in a second. N, O, and F have the highest electronegativities. They're all they're all in order there. Actually, chlorine does too, but there's something special, as we talked about, in the hydrogen bond with NO and F. Okay, let's go to 11. Oh, the chemists like these fancy terms. They like these fancy terms. So a dipole moment, it's a special moment because you get separation of charge. So you're forming a positive pole and a negative pole, and that's called a dipole moment. So that occurs in any polar bond or any dipole. So like here's a dipole moment. You end up with a slightly positive end and a slightly negative end with which HF. So, but know the term dipole moment. Okay, occurs when there's a separation of charge forming a positive pole and a negative pole. Okay, we go to number 12. Oh my goodness, how important this is in nature. And you should know this in your sleep. Water is a V shape or angular shape or bench shaped. It is a polar molecule. This side is slightly positive, that side slightly negative, and that's going to explain all the important properties of water. And without these properties, life would not be possible on the earth. Hugely important. You should know that water is angular shaped and it's a polar molecule. Okay. Now, sometimes you can have a nonpolar molecule even though it has polar bonds, because they cancel each other out. And one of the examples we gave was carbon dioxide. Carbon dioxide is linear. It's the same on both sides of the carbon. They cancel each other out, so it's nonpolar. And you should also know the shape. So if I said to you, is CO2 polar or nonpolar, you should know it's nonpolar. If I say to you, what's the shape of CO2, you should say it's linear. Okay, and you can also tell that by drawing out the electron dot formula, which we'll review shortly. Okay, now these are some other cases where you have nonpolar molecules made up of polar bonds because they cancel each other out. So here's CO2, we just talked about that, and then SO3 is in this shape, which you should recognize as trigonal planar, and so they can't, the different bonds cancel each other out. You got three polar bonds that cancel each other out, nonpolar. And then CCl4 is tetrahedral. You should know it's a pyramid shape, but it's also nonpolar because it's the same all the way around. So these three molecules, although they have polar bonds, they all cancel each other out and they're all nonpolar. So if I said to you, is CCl4 polar or nonpolar? You should say it's nonpolar. CO2, nonpolar. SO3, you'd have to draw the electron dot formula, and you'd see that's going to end up with this type of a shape, and therefore there's no lone pairs, and so it's trigonal planar, and it's nonpolar. Okay. 16. Okay, it's sticking. Let's move on this thing. Come on, babe. There you go. Oh, beautiful. Love this slide. Again, you should know this term, valence electron. So important. Pardon me. Sorry for clearing my throat there. I always have this congestion from nasal drip. So sorry about it. I have to clear my throat from time to time. Sorry about that. It's not pleasant for you as a listener. So the valence electrons are the outer shell, and they're so crucial because that's where the action takes place, isn't it? That's where electrons are shared or transferred. Okay. And remember, in the old system of naming the columns, which I like so much, what's so cool about that is the column number for the A columns, the tall columns, tells you how many valence electrons. So the first column, the first family, has one valence electron. The second one has two valence electrons. The third one has 3, 4, 5, 6, 7, and the last column is 8 except for helium, which only has 2. Okay, so that's very important. To figure out the number of valence electrons, you just look at the column number. Very, very useful. And that's why I like that one so much. I don't like the new system. They didn't ask me. They should have. I would have said, don't do it. Okay, but you're always given both the new system and the old system, so you don't have to worry. On the periodic table that it'll have the A, and so you'll know that's the one you use for the number of valence electrons. Okay, I think that's number 18. So remember that what the atoms want to do when they combine is to get a noble gas configuration, either a duet in the case of helium or an octet and all the other, and match the noble gases. So when two nonmetals share electrons, that's what they're trying to do, as we know. And the same thing is true of ionic. By giving away electrons and receiving electrons, they want to end up with 8 in the outer shell, a noble gas configuration. Okay, let's go to number 24. Number 24. And just as we learned earlier in the year, metals in group 1A lose 1 electron. Group 2A, they lose those 2 electrons. In group 3A, they lose 3, because then what's left, the new shell is full. And that's what they're after. And then in the same way, the nonmetals in group 7A, they gain 1 electron and achieve 8. And those in 6A, they have 6, and so they gain 2 more. So they form a -1 and a -2. So that's something we learned early in the year. Now we know why that happens. Okay, that's 24. And let's go to number 20. This is very important now. There will be a question about this. And it should be easy if you just think about it a little bit. Cation is always smaller than the parent. Here's the parent atom, sodium. It has 3 shells. It loses its 1 electron in the outer shell. Now it only has 2 shells. It's smaller. Okay, so the cation is always smaller than the parent atom. Conversely, the anion, negative ion, it has gained an electron, and so the outer shell expands, and so it's bigger. So the anion is always bigger than the parent atom. More examples. Oops. What happened there? Went too far. Here we were. Okay. So this makes it very clear. It loses the outer shell, and so the cation, the positive ion, is always smaller than the parent ion. And here are some other examples where the cation is smaller. Conversely, here are examples that show you that the anion is bigger. When it gains an electron, the outer shell when it gains 1 electron, the outer shell expands, and so it's bigger. The anion is bigger than the parent atom, the neutral atom. Okay? So there will be a question on that, and it should be easy if you just think about it a little bit. Okay. So that's slide 26. Keep going here. Okay, another term that you need to know, isoelectronic. Isoelectronic means they have the same number of electrons. And what you should be able to see, and I went through this, I'm not going to go through it now again, but O, -2, F -1 have the same number of electrons as neon. They're isoelectronic. And not only that, sodium ion, magnesium ion, and aluminum ion also have the same number of electrons as neon, and so they're all isoelectronic. What's iso mean? Same. Isoelectronic means they all have same number of electrons. Okay, and then 30. Whoops. Yeah. Now, the driving force, I said, for atoms to combine, either share or transfer electrons is to get an octet. But we can even go one step deeper. When they do that, they become very stable and they're at a very low energy. It's sort of like a ball reaching the bottom of the hill. The ball's falling down the hill and it reaches the bottom and it stops moving. It's stable and it's at the lowest energy point. So you could say that's the driving force. That's why it wants to form an octet or a duet, because it's more stable and it's at lowest energy. And by the way, let me add, that's how God set things up. Some atheists try to say, well, that's the reason why these things happen, because they want to get the lower energy and they want to be more stable. Well, why? Why? Because that's the way God set things up. All right? But they do. Once they get that octet, or once they get, full outer shell, they are very stable and they're at a very low energy state, which is good, which is stable. All right, now, don't get this wrong, please. Don't get this wrong. There's no quadruple bond. You can have a single bond, 1 pair of electrons shared. A double bond, 2 pairs of electrons shared. A triple bond, 3 pairs. All of these exist in nature. But there's no situation where you have 4 pairs. So quadruple bond does not exist. Don't get that wrong, please. Okay. Now, sometimes this happens. This is supposed to be a bullet. It shows number 4, but I don't know why it does that. Anyway, some pairs of electrons are not shared. They're called lone pairs, and as we learned, they have enormous impact on the shape. If they're not bonded, they're called either unshared or lone pairs. And if they are bonded, they're called bonding pairs. Then we get into our electron dot formulas. Remember, we're only looking at the valence electrons. There has to be one valence electron on each side before you pair them up. The symbol represents the nucleus and the rest of the electrons, the core of the atom. And I gave you this handout. See if I can get to it. Let me do it this way. 39 is here. Okay, so this is a very good thing to try to understand. Remember, you have to have one dot on each side before you pair up. So beryllium does not have a pair of dots together. They have to be separated. You don't see the pairing until after 4 dots, and then you get one pair and then the next pair and so on. So be careful of that. So you should be able to recognize the electron dot formula for any element in the table just by looking at what column it's in. And I'm only going to ask you about the tall columns, not the transition, okay? So it should be very easy. You should be able to recognize, and that has its own methodology. Single elements, you just use the method that I told you. Okay, let's see, was it 39? That's 39. And then let's go to 42. Now, when you get to molecules, you have to follow another method to figure out the correct electron dot formula for a molecule. So there might be a question or two saying, is this the correct electron dot formula for this molecule? So what you have to do is 2 things. One, you got to find out the total number of valence electrons you're starting with, and you have to end up with that same number of electrons. And number 2, each atom should have a full octet of electrons. Both of those are true, then it's a correct electron dot formula. And by the way, that's the way it is in nature. It reflects correctly the way the molecule exists. If you don't have that, then it's not correct. So you got to have 2 things have to be true. When you're looking at the electron dot formula for a molecule, you have to have the correct number of total valence electrons for all the atoms involved, and each atom has to have an octet unless it's hydrogen, which will then have a duet. Okay, and so what I just said, I spell out here in slide 45. Okay, so you add up the valence electrons, you use a pair of electrons to form a bond between each, and then you arrange the remaining to satisfy the duet rule and the octet rule. Now for the exam, it's just going to be recognizing, you'll be given the electron formula for a molecule. You'll be given 4 choices, and only one of them is correct. So then you don't have to draw it out, you just have to recognize those 2, make sure those 2 rules are met, these rules that are mentioned here. Now, in slides 46 to 54, which I'm not going to go over now, there are examples of electron dot formulas for molecules using this method. And by the way, Alana asked a very nice question. This is a different method than used for individual elements. Individual elements has its own method. Molecules, we got to follow this method. It's different. I'm very glad that she asked that question. This is a different method, but it works. This method works to describe the way molecules are built in nature. And that's why it's a work of genius by Mr. Lewis. A work of genius. Okay, now, you should know, another term you should know, resonance. Sometimes there's more than one valid Lewis dot structure, and that's called resonance. And so we give an example here of NO3, and notice that we say really what it is, it's in between a single and a double bond, so we draw it like that. All right, but any one of these is correct. a correct Lewis structure. And notice the shape is trigonal planar, right? Trigonal planar. There's no lone pairs, and so it's called trigonal planar. All right. Let's see, that's slide 57. Let me go to 5. Then we go to, then we have the fun with the shapes. So I'd like you to know the shapes of, given the molecule, given the chemical formula, tell me what shape it's going to be. So, let's see here. So again, the VSEPR theory, the valence shell electron pair theory, what it's there to do is tell you, what it's there to do is you want to minimize electron pair repulsions. So the electrons try to get as far away from each other as they can. So electron pairs, whether bonded or non-bonded, try to get as far away from each other as possible. Okay, so we mentioned, whoops, what happened there? Keep going. Okay, so we mentioned, whoops, this thing's just messing me up. Go away, hold it, delete that. Okay, good. All right, because I have my numbers. Okay, so slide 63, remember tetrahedral shape. 4 pairs of electrons and 4 atoms, like CH4 or CCl4. And this tetrahedral shape comes for elements in the 4th column, the 4th family. Basically carbon or silicon form this tetrahedral shape. 4 pairs of electrons, 4 atoms. So if I say to you, what's the shape of CH4? Tetrahedral. What's the shape of SiF4? Tetrahedral. That's the kind of question. And then we go to the next one, 65, trigonal planar. How do you recognize trigonal planar? Well, one way is boron. Remember, boron is the exception to the octet rule. And so you have 3 pairs of electrons and 3 atoms, and that shape then is going to be trigonal planar. And that basically is, here's another example of it. Now, but then you get a case where you've got 4 pairs of electrons. Oh, excuse me, that's trigonal planar again, same thing. And again, it has to do with boron. But what I wanted to get to was a case where you have 4 pairs of electrons, but only 3 atoms. And so you end up with a lone pair. And this is going to involve nitrogen and phosphorus, which is column 5A. And notice the electron dot formula looks like that. And this lone pair is not bonded, and it causes it to have the shape of trigonal pyramidal. So you should know, if I said, what's the shape of PF3? You should know it's trigonal pyramidal because P is in column 5. Electron dot formula looks like that. And you end up with this lone pair which repels the other bonds and makes it into a little pyramid shape. And it's not flat because of the lone pair. That's 68. And then I want to go to 70. We compare the two. Both of these molecules have a central atom with 3 surrounding atoms. What's the difference? The trigonal pyramidal has this lone pair where there's no lone pair in the trigonal planar. Okay. So that's 70. And then we go to 71. Again, you should know water is angular. In this case, it's got 2 lone pairs which repel the other bonds and make it into the bent shape. Sulfur behaves the same way, so this one to be column 6A. They form this bent shape. Here's a case of linear. You've got 2 pairs of electrons with 2 atoms, and so they form a linear shape. And then carbon dioxide, if you write the electron dot formula, you'll see that it has 2 double bonds It's the same on both sides. There's no unshared pairs of electrons on the carbon, and so it's going to be linear. And here's comparing carbon dioxide with water. They both are made up of 3 atoms, but this has 2 lone pairs, so it's bent. This one doesn't. Carbon doesn't have any on the central atom, and so it's linear. And of course, any diatomic are linear. By the way, notice this has a double bond, this has a triple bond, and this has a single. And if you follow the rules for electron dot formulas for molecules, you'll see why these work. Each ends up with 8, and you have the same number of valence electrons at the end that you started with. Okay, so that's 75. Let's see, 76. So in determining the shape, you need to draw the electron dot formula and follow these rules that are found on this slide. Again, here's your tetrahedral, trigonal, planar, and linear. There's no lone pairs in these cases. Then I give you this chart, which you should go over carefully. And I give you examples. So I give you the number of pairs of electrons, number of atoms around the central atom, the shape, whether it's polar or nonpolar, and examples. So any one of these I could say, okay, BeCl2, I could say, what's the shape of that? And you should realize that it's going to be linear, and is it polar or nonpolar? Nonpolar. The same thing for these, okay? So you should know this chart. Is it 80? And then let's see, 81. Oh, yeah, another way to look at this is the number of lone pairs. So if there's no lone pairs, it's either going to be linear, trigonal, planar, or tetrahedral. If there's one lone pair, it's going to be trigonal, pyramidal. If there's 2 lone pairs in the central atom, it's going to be angular. And then in 83 to 87, I talk about multiple bonds, the shapes of molecules with multiple bonds. And then on 90, let's see, what's slide 90? I talk about, I'll give you some examples, some practice examples. You should go through and be able to give the shapes and whether it's polar or nonpolar. That's slide 90. Okay.